In this question it is given that A and B are 2 points on a uniform metal ring whose center is O. The angle AOB is equal to theta. So if you are just considering a uniform ring with 2 points, let's say point A and point B, and this angle is given as nothing but theta. A and B are maintained at two different constant temperature. Let's say A is maintained at a temperature T1 and B is maintained at a temperature T2. When theta is equal to 180 degree, the rate of total heat flow from A to B is 1.2 volts. So when the value of this theta is equal to 180 degree, that means let's say this one is representing point A and this is point B, and there will be some heat flow from A to B and through this path or through this path. So the net flow of heat energy is given as nothing but 1.2 volts. So here you can just consider that situation is similar to a situation in which here we are having a resistor of resistance R, and here we are having a resistor of resistance R, and current is flowing through both the resistors. So over here we know that equal amount of current will flow through both the resistors, or you can just consider that is a parallel combination of resistors. So over here you can just consider that its equivalent resistance of this combination can be taken as something but R divided by 2, and if you are maintaining some potential difference, let's say delta V, then the value of current flowing through this one, we can just consider that the value of current is potential difference by resistance, that is delta V by R by 2. So it is 2 delta V by R will be the value of current initial. So this value is similar to that of heat flow rate, which is 1.2 volts. Now in the question it is given that when we are changing the value of this theta to 90 degree, that means we can just consider that this one is, let's say, the point A and this is point B, in such a way that this line is making an angle 90 degree. So there will be some amount of flow of heat energy from A to B through this path as well as through this path. Now we know that as the value of resistance is directly proportional to length, and if we are considering the resistance of region from A to B, so we can just consider that there are two resistors of resistance R1 and R2 are connected between point let's say A and B, which were maintained at different temperatures. So take it as the resistance of this one as R1 and R2. So in the initial case we consider that resistance between A to B is R. So over here the length from A to B is more than R, so its resistance will be more, and the resistance of this R2 is decreased because its length is half of its actual length that we consider. So we can write resistance of this one can be taken as nothing but R divided by 2 compared to the initial resistance that we are taking, and resistance of this one can be taken as nothing but 3R divided by 2. Now we can consider that these two resistors are connected in parallel, so we can write the equation for its equivalent resistance, that is R1 R2 divided by R1 plus R2. So if you are finding out the value of equivalent resistance, then it will be 3R by 2 into R by 2 divided by R1 plus R2, that is equal to 2R. So this equation becomes equal to nothing but 3 divided by 8R. So we can find out what about the value of current flow now, that is potential difference divided by resistance, which is 3R divided by 8. So now the heat flow becomes 8 by 3 times of delta V divided by R. The initial heat flow was 2V by R, so which can be written as nothing but 4 by 3 into 2 delta V divided by R. The value of 2 delta V by R, we know that that is 1.2. So we can find out the value of this heat flow over here, that is equal to nothing but 1.6.